In this problem, we have a fence that's 12 feet tall. That would be this right here. And it runs parallel to a tall building denoted by this vertical red rectangle. And it's known that the distance between the fence and the building is 3 feet. That's denoted right here. So again, the blue vertical line is the fence and the red rectangle is the building. The problem we're trying to solve is to find the length of the shortest ladder that would reach from the ground right here over the fence, which is this blue vertical line, and actually reach the wall of the building. To use right triangle trigonometry, I notice that there are several potential right triangles. We have this medium-sized triangle here with side 12 feet. You could pen in a smaller triangle right here. This length would be 3 feet, and the hypotenuse would be the second part of the ladder. And I guess one could argue that there's a large triangle that looks like this, whose hypotenuse would be the length of the ladder. Those are just some things that come to my mind as I start to try to figure out how to solve this problem. To find the length of the shortest ladder, I'm going to define a trigonometric equation that represents the length of the ladder and then just minimize it. So let's start with that medium-sized triangle. I'm going to use this red triangle whose hypotenuse would be not the length of the whole ladder, but at least part of the ladder. Then I'll use this purple triangle whose hypotenuse would be the second part of the ladder. So if you added the length of the hypotenuse of the red triangle to the length of the hypotenuse of the purple, you would get the full length of the ladder. Because the picture is quite convoluted, let me drag the red triangle and the purple triangle off of the diagram and we'll start labeling it. So one thing you can see in the picture right here is that one side of my red triangle would be 12 feet and we would know that the angle is theta. So according to the diagram, this is theta and this distance here is 12 feet. Let me let lowercase a represent the length of not the entire ladder, but just that first piece that I've highlighted in yellow. The trig function that would relate theta, the opposite side of theta, and the hypotenuse would be, of course, the sine function. We have that the sine of theta would be the opposite side, which is 12, over the hypotenuse a. So if I want to know the length of not the entire ladder, but the portion that I highlighted in yellow, we'd have to solve for a, since I'm letting a be that length. If you let me multiply both sides by a, I get that a sine theta is 12, which means that a is 12 divided by sine theta. And again, that's not the length of the entire ladder, that's just the first piece. I'm breaking it up into two pieces. The second part of the ladder would be this distance here, and I suggested we use this purple triangle whose hypotenuse would represent that length. So I'm going to call the length of the hypotenuse of the purple triangle b, and from down here you can see that this side would be 3 feet. Now you might be wondering, in this right triangle, what variable I may pick for the angle. It turns out that that angle is the same as this angle, theta. In geometry, there's a theorem that says if you have two parallel lines, I drew two red parallel lines, if they're cut by a transversal, that's my blue line, then corresponding angles would be congruent. In our picture, we're talking about this angle and this one. In the picture, they have this angle labeled as theta. By the theorem in geometry, this would also be theta. So to show you that that is indeed what we have in our picture, let me draw those two parallel lines. Here's one of them. Here would be the second one. And for some reason, the software is not letting me draw the line right where I want it, but you get the idea. And the transversal actually is the ladder itself, which I'm drawing in blue here. So once again, the angle theta right here would be the correct label for where I drew the question mark. Since we have two parallel lines cut by a transversal, not only is this angle theta, but this one would be as well. So I made a copy of the purple triangle just because the diagram is getting complicated. Now that I've argued that this is theta, we know this length is 3 feet, and we're trying to solve for the length of the second part of the ladder, which I labeled b. Given this setup, the side with length 3 feet would be the side adjacent to theta, and of course b is the hypotenuse. So we'd use the cosine function and say the cosine of theta is the adjacent side, which is 3 feet, divided by the hypotenuse, which is b feet. If you let me multiply both sides of the equation by b, you would have b cosine theta equals 3, and then since the b is being multiplied by cosine theta, you'd solve for b by dividing the cosine theta over. So now I have a trigonometric expression for the length of a and the length of b, and remember if I sum a and b, I get the full length of the ladder. So the ladder's length, I'm going to call L, is simply the sum of length a and b, but we found a to be 12 over sine theta, b was 3 over cosine theta. So let me just paste that in right here. So now I have a formula for the length of the ladder. So what this means is we can construct many ladders by varying theta. But I'm going to find the theta that minimizes the length of the ladder. I'm going to do this without using calculus by just graphing it on my calculator. So let me press y equals, and I'm going to type in 12 divided by sine. Now in this mode of the calculator, normal mode, I have to use the letter x for theta. So just remember the variable x in my problem is theta. And the variable y, or if you want y sub 1, in my calculator is the length of the ladder. So that's the first part of the ladder, and now we have to add the length of the second part of the ladder, which was 3 over cosine x. So knowing that my input x is theta, the angle, and my output y is the length of the ladder, that'll give me some clue as how to set up my window. For example, when I click my window here, it makes no sense for theta to be negative 10 degrees. I'm in degree mode. You could also do this in radians. But in degree mode, it makes no sense for the x-min to be negative 10 degrees. If you look at the picture, obviously theta is between 0 and 90 degrees. I'm not sure you'd have to go as far as 90, but you could. I'll put in 90 just to see what happens. And then remember my y, min and y max, the letter y represents the length of the ladder. I have no idea what that length could be. I'm not suggesting the picture is to scale, but since this was 12 feet, I mean, it looks by the picture that the hypotenuse would be like 15 or something like that. But remember that we can vary theta and get variations on this triangle. So just as a stab in the dark, let's try 50 feet. And I guess I should change my y min to 0 since it makes no sense to have a ladder of negative length. In fact, it makes no sense to have a ladder of length 0 either, but we have to start somewhere. I'm just going to hit graph and see what I get, and I may have to alter those numbers in my window depending on how this comes out. Okay, so I'm seeing a definite minimum on the graph, so I don't need to change my window. You could get an estimate of the answer by just pressing trace and scrolling over to where the minimum appears to be. So somewhere around 56 or 57 degrees, that is the angle that produces the ladder of shortest length, and that shortest length is around 19.8 feet. But we want to use the full accuracy of the calculator. In fact, the directions would round the answer to 3 decimal places, so I want to use the full accuracy of the calculator to get this minimum. So to do that, I'm going to press second, the trace key. Minimum featured is number 3. Either just press 3 in your keypad or scroll down, press enter. The calculator is going to ask 3 questions. It's going to ask for a left bound, which means it wants you to trace to the left. And since we're dealing with a minimum, not only is the left bound going to be a point to the left of the minimum, it'll also be a little higher. So as long as you're convinced that you're to the left and higher than the minimum, that would be a good left bound. I'll press enter. And then the right bound is the same thing. You just trace to the right. And again, since we're dealing with a minimum, not only would you pick a point to the right of the minimum, but you'd also be higher than the minimum. I'm convinced that my point is both to the right and higher than the minimum, so I'm going to press enter to define that as a right bound. Now the computer is going to search in that region that you just specified between those 2 vertical dashed blue lines, and it's going to find the minimum. It wants you to guess, so you could trace to the left and guess what it is. I oftentimes tell students not to do that because their answer is pretty accurate at that point, and they forget that this is not information the calculator is giving you, it's information you're giving the calculator. So students may get an answer that's close, but not be using the full accuracy of the calculator. So you do want to press enter at that guess prompt. You don't want to see the word guess as your final answer. You want to see the word minimum. So the minimum is when theta, or x, is about 57.791 degrees. But the question didn't ask for the angle, it asked for the smallest length. So the smallest length in our units were in feet is 19.811 feet. I'm not sure how easy it is for you to see this, but the digit to the right of the 0 is a 9, so I'm going to round the 0 up to 1. So 19.811. And again, the length of the ladder was in feet. So I hope this helps you make your way over your fence and reach your building.